Hello, good afternoon, everyone. Welcome all the attendees to the special symposium on material informatics. My name is Apinya Panupat from MTech, the National Metal and Materials Technology Center at NASDA in Thailand. And I'm very pleased to be your MC today to conduct the program on the symposium on material informatics. We are focusing on the accelerating materials research using artificial intelligence. So before we begin shortly, I would like to go through a little bit about the program or the speakers that we are having with us today. First of all, we'll have the welcome and opening from our executive at MTech, Dr. Ari Thanapunsombat. And then after that, our first invited speaker from Singapore, from A-Star, Dr. Tan Teck Liang. He will present on the topic of designing alloys and high entropy materials via machine learning. After Dr. Teck Liang, we'll have Professor Dawei Chang from China, from the University of Science and Technology, Beijing. He'll present his research on the intelligent corrosion control via data-driven approaches. After the two talks, we'll have a short 10-minute break. And then after that, we'll hear from Dr. Nongnut Adrit. She's the assistant professor at the Utrecht University in the Netherlands. She'll talk on the overview of the machine learning approaches, especially on the applications of for energy materials. After that, we'll hear from two of our researchers here at NASDA, Dr. Tongchai Chukajon from MTech and Dr. Vanida Pongsaksawat from RMT, the Rail and Modern Transport Research Center. Under NASDA, they'll introduce the current trends in materials informatics for material research at MTech and MRT. And then I will finish with my short presentation on the program, on the training scheme that our team of researchers here have for the materials community in Thailand to equip our researchers and with the AI tools capabilities. We have some training scheme for you. Okay, so that's the program for today. And I hope everyone is ready, and thank you so much for your overwhelming response to attend this special program. And let me invite before we begin, I would like to let everyone know that during the talk, if you have any questions or any comments or any question for the speakers, please type your question in the chat box, and we have our team to collect all the questions and then ask the speakers for you at the end of each talk. So you can write in English, in Thai, so that will be a team of our team taking care of the question for you. So first of all, before we begin the talks, I would like to invite our Deputy Executive Director of MTech, Dr. Ari Thanapunsombat, to give the welcome and opening speech. Please, Dr. Ari.
Thank you, Dr. Pinya. Good afternoon, everyone. It is a great pleasure for me to welcome you, the participants and speakers of this special symposium on materials informatics, accelerating materials research using artificial intelligence. This symposium is organized in conjunction with the 11th International Conference on Material Science and Technology, or MSAT 11. This year's conference is co-organized by co-partners, which are MTech, the National Energy Technology Center, or NTech, the Technology and Informatics Institute for Sustainability, or TIIS, and the Rail and Modern Transport Research Center, or RMT. During the past 2 days, as well as today, some recent progress and R&D activities ranging from fundamental research to applied research in material science, technology, and engineering have been discussed and shared virtually. among the conference attendees. In addition to these, there are 3 special symposia held during this event on technology frontiers in well-living, megatrends in future mobility, and here this afternoon, a symposium on material informatics. The title of this special symposium, Accelerating Material Research Using Artificial Intelligence, is very much fitting with the challenge that materials communities across the world have been facing during the recent years. The challenge is to develop new materials technologies at a faster rate. And such developments must be in a more cost-effective way than previously done. This challenge involves reducing development time, both for the discovery of new materials and the prediction for their properties and process. During the past few years, we have witnessing initiatives, new and innovative policies, and enormous support for R&D ecosystems in different countries to drive this emerging research discipline of materials informatics. In leading academic institutions across the world, we observe new course offerings, both at undergraduate and postgraduate levels, aiming to incorporate fundamental knowledge and capability in informatics for the future materials workforce. For the current material professionals, training and upgrading the skills necessary for materials informatics is becoming vital. Not only we are observing the acceleration of the expansion of knowledge, but essentially, we as material scientists and engineers are also participating in advancement in materials technology that may not be possible to achieve before. New technologies, new multidisciplinary research areas, international collaborations all contribute to moving materials community forward. It is an honor for us to host this symposium in this time of important technological transition. I am pleased to learn that this symposium has received wide interest from the academia, research institutes, and from the industry as well. Looking at today's program, the session offers a unique opportunity to hear recent developments on data-driven approach for corrosion control, on machine learning approach for designing materials, looking at the case of alloys and energy materials. I would like to extend a very warm welcome to our international guest speakers, Dr. Tan Teck Liang of the IHPC A-Star in Singapore, Professor Ta Wei Chang of University of Science and Technology Beijing in China, and Dr. Nongnut Atrit from Utrecht University in the Netherlands. I would like to thank them for accepting our invitation to this symposium. I hope that they will enjoy some discussions with our participants later on during this the section. And I would like also to congratulate the organizers of this symposium on their initiative and their ongoing efforts in devising and supporting skills development among the local materials community. Ladies and gentlemen, thank you for your time. I wish you all a good symposium this afternoon. At this auspicious moment, may I now declare the symposium open. Thank you.
Thank you very much, Dr. Ari. Thank you for your kind words. And before we begin with our first talk with Dr. Teck Liang, can I ask every attendees to please take this opportunity for the photo ops and turn on your camera and take a photo together, please. Okay. I see some familiar faces there, and yes, welcome everyone to the symposium today. Okay, our team's ready to capture some photo there. Okay, I think we are good with that. So let me first begin by introduce our first speaker, Dr. Tan Teck Liang. Can I say hello from Bangkok to Singapore? And before his talk, I would like to say a few words about his background and introduce Dr. Teck Liang to everyone. Dr. Tan Teck Liang from A-Star IHPC. His background is in mechanical engineering. He did the bachelor degree at the National University of Singapore, and then continued for his PhD in material science and engineering with the specialization in computer science and engineering there at the University of Illinois at Urbana-Champaign in the US. Since 2019, he has been joining the innovative lead. He's been the leader of the accelerated materials and chemical development at A-Star. And at the moment, he's the department director of the material science and chemistry department since 2022, sorry. And before that, he has been the group manager leading a few researcher team in the area of alloys and materials design, which is his specialization. So I think it's very fitting that we have him here today to talk about his research and his work about the data-driven and machine learning for designing alloys and the high entropy alloys there. Please, the floor is yours. I mean, the screen is yours, Dr. Teck Liang. Please share your screen. Thank you.
Thank you, Apinya, for the kind introduction, and thank you, MTech, for the invitation. Let me try to share my screen. Let me see. Okay, I will go to maximize the screen. Everyone can hear me and see my slides?
Yes, I can see you quite perfectly. Thank you. Okay,
thank you. Yeah, so I will proceed straight to the presentation. So, so today I'll be talking about designing alloys, especially high entropy materials via machine learning methods. Okay. All right, just a couple of slides to introduce the institute that I come from. It's IHPC, Institute of High Performance Computing. So this is a research institute under A-Star Singapore. So we have about more than 400 researchers, and it was established in 1998. So we do basic research, and also we collaborate with industry and companies. Yeah, because over here, our mission is really to look at going from scientific research and then translating it into applied research, and also serving the industry in Singapore as well. Okay, so here are the departments in my institute. So we have 7 departments. 3 of them is more on the, we call it the more link with the computer science. So we have a system science department, social and cognitive computing department, and computing and intelligence department, whereby our colleagues use various models of artificial intelligence and machine learning to help accelerate discovery in many different areas. And we have 4 engineering departments as well. So material science and chemistry is where I come from. There's also engineering mechanics, fluid dynamics, and electronics, photonics. So as Dr. Eric pointed out, for science and engineering, we are also increasingly seeing more and more applications of AI, machine learning, data-driven approaches to help us to accelerate our modeling and simulations. And indeed, we also work very closely with our com science and computing and intelligence departments to develop all these tools for accelerating materials discovery. Okay, so this is the department which I'm leading. So we have modeling and simulations, and more recently also data driven approaches to design various materials for different applications and also for different needs from the industrial sectors. So we have a group which is working on alloys, looking at developing methods, multi-scale simulations for designing alloys, looking at metallurgical properties, prediction of stability and microstructure, and looking at corrosion, electrochemistry as well. We have also a chemistry and catalysis team doing modeling and also using this for reaction mechanism studies and catalyst materials development. We have a soft material polymers and formulations group, which does a lot of this molecular kind of simulations in order to understand the properties of the polymers and formulations, and using this to design new formulations to help our companies and our stakeholders and experiments to develop new specialty chemicals and formulations. And we also have the electronics and semiconductors group, which has a lot of work on semiconducting materials, from things like silicon and also heterogeneous materials, 2D materials, looking at their surface chemistry, looking at defect size, and also thin film growth as well. And recently, we also have a quantum computing group, which is developing algorithms to ready ourselves for the possibility of quantum computing coming into our computational space, right? Okay, so I will start the presentation proper on looking at data-driven materials discovery. So these are the trends that that has been ongoing for some time, dating back to 2011, whereby in the US, there was this initiative called the Materials Genome Initiative, and that has also spread worldwide as well, whereby through this initiative, there's a lot of materials data that's being generated, be it through computation or be it through experiments. So over the years, so I list some of these examples over here. There are large databases of materials. There's this materials project, OQMD, Atom Work from Japan. So I think materials project was developed from the MIT group. OQMD, I think, is from the Northwestern University. Yeah, so all these are open source, and you can access materials data from it. I think materials project and OQMD, they are based on first principles DFT calculations. Yeah, and Atom Work, I think they have experimental data as well. So there is a lot of the data on materials out there, and that also leads us to develop new approaches for materials design, especially if we have data. We can leverage on some of these machine learning and AI in order to accelerate the discovery of new materials. Okay, so these are the important components for materials design, from database management, and using AI to learn about our data and use it for knowledge creation and discovery. This is a picture of how we attempted to do it in one of our programs on catalyst materials development. So our team, our catalysis design team, they working closely with experimentalists from one of our partner institutes. We're trying to develop this accelerated catalyst development platform. So you can see that there are three critical pillars over here. On the left, you can see that there's a pillar about developing computational workflows so that you can do high high throughput screening so that we can quickly, using supercomputer technologies, using them to generate a lot of this computed data. And in the middle itself, there is the development of more realistic models. So the idea here is that when you're doing catalysis modeling, there's many different components. There's the active catalyst itself, there's also the catalyst support, and there is also the promoters as well. So are we able to use AI to accelerate the discovery and the design of these complex catalyst materials? So in it, there's a lot of usage of using AI to learn from DFT calculated properties, DFT calculated data, and then use that to create this kind of interatomic potential interactions, and that can help to accelerate the computation of materials properties. And we also work very closely with experimental partners to apply machine learning on their experimental data set. And increasingly, we're also using computed data set and add it to the experimental data set so that we have more data to train on, and together, hopefully we can develop a more accurate and robust machine learning model for catalyst development. And it's also important that besides looking at the besides the science, in order to do machine learning in an effective way, we also want to develop platforms because the infrastructure is also important. Over here, what we were trying to develop is that we're trying to develop the platform so that it will be easier for general users to use this machine learning model for their own discovery. So you can imagine if we develop a model, and let's say we have some GUI, graphical user interface, to allow users to quickly use a model to design their own experiment. This can help to allow more people to access, more people to use AI technology in their research. So this is our vision. This is our aspiration. We hope to, through maybe multiple projects, to work to develop a platform over time, which can allow users, modeling and simulation people, and also the experimentalists to come together to share their data, and also for the AI folks to share their codes, so that together there will be a platform for different users to cross-share their data and use the various models for discovering new materials, be it for alloy applications, catalysis, or formulations. All right, so these are very broad pictures of some of the initiatives and programs we have over in A*STAR that is leveraging on AI and machine learning to do materials discovery. Okay, so I will go into a specific topic that is using machine learning to accelerate alloys discovery. So we know that some of us might be familiar with this term called first principles calculations. So this is based on quantum mechanics, and typically if you build an atomic structure and if you put the elements on the structure, we can use a DFT, first principles calculations, to calculate their properties. And generally, this is a very we have codes, we have software which is available, which allows us to quickly do some calculations to verify the structures and their properties. But we know that these calculations are typically expensive, and in terms of alloy design, we would have a problem when when we are dealing with alloys, because for alloy design, depending on how the A and B atoms arrange, they will give us different properties. So over here below, this is a phase diagram of a typical binary alloys. And depending on how you arrange the A and B atoms, they will give you properties. So at higher temperatures, you can see that because of entropy, the arrangements of the A and B atoms is more disordered. And as you go to the lower temperatures, there's more ordering, and depending on the composition, the ordering can be different. And typically, what we want to understand is, what is this phase boundary? What is the phase boundary? What is the temperature at which the phase would switch over from an ordered phase to a disordered phase? So this is a very fundamental question that we have in alloys design, because going from different phases will give us different properties. And this is a slide to say that there are so many different configurations. So if we are just using first principle calculations, which is very computational expensive, we will not be able to calculate all these different arrangements. And therefore, we have a method to develop what we call the surrogate model. So you can imagine, we can start off with the first box. You can have maybe calculations of maybe 100 DFT calculated structures. And then the gray over here is just a particular method to create this machine learned surrogate model. So you take about 100 structures, and then we can train them in order to get effective interactions. And once you have the machine learned model, you can go through millions of different configurations, and that allows us to use Monte Carlo simulations to model the phase diagram. And on the right, you have this evaluation of more than a million configurations to identify which are the stable ones. Right. So in the alloy design space, we have, for example, demonstrated that we can use this kind of machine learned surrogate models to discover the phase diagram of alloys, be it for the ordering type, which is on the left, or be it for the segregation type, which is on the right. So now, knowing that we can use this kind of methods, machine learned surrogate models, to study alloy thermodynamics, then the next question is, can we use it for more challenging problems? Can we say, for example, use it to design high entropy alloys, which is a mix of 5 or more different elements? And can we use that to, say, design nanoparticle alloys as well? So you might be wondering why high entropy materials and high entropy alloys. So unlike conventional materials, over here, if you look at the right, this is a atomistic model of a high entropy alloys, whereby you have 5 or more different elements, and they are of approximately equal composition. And this typically tends to stabilize the disordered, we call it the disordered structure, or the random solid solution. Yeah, but nowadays with new design rules, it doesn't always need to be the case. In the HEA, or high entropy alloys community, we also increasingly, people are trying to tweak or change the composition so that there can be secondary phases that is being formed, and this will help to use this will help to strengthen the materials. And if you look at the right, this will show that, okay, entropy, the high entropy alloys has certain promising characteristics. Yeah, so they can be, we can design high entropy alloys with high toughness and high yield strength. Right. So some of the points that I want to show here is that high entropy materials, they have found structural applications, and increasingly researchers are also using them for to discover their to use them for functional properties like catalysis and for batteries as well. And the design space is really large over here. You think of 5 elements and you think of the periodic table, there are so many ways of choosing the combination of elements, right? So there is a very big, very huge discovery space for designing high entropy alloys. This is a bit looking at the surrogate model. We use a particular model or methodology called the cluster expansion method. So if you look at the equation on the left, it's just to say that we have the energies calculated from the DFT first principles calculation. So E is actually the energy is known, and on the right we're trying to say that we can expand this energy in terms of atomic clusters. So this can be this sign here called phi can be known as well. We can count the number of, say, BB atoms and BBB triplets and so on. So these are atomic clusters. And what is unknown is we call it the effective interactions. For example, V can be a bond, can be a pair interaction between the B and the B atoms, right? So we have, what we are trying to do over here is to get the effective interactions V. So, so one technique that we really use is to use this group Lasso to train this machine learning model in order to get reliable interactions V. And this is on the right is a parity plot that we show that, okay, our predicted energies is actually very close to the first principles calculated energies. All right. Again, over here, this just to illustrate, if you look at the diagram on the right, so these are the kind of clusters that we have in our cluster expansion model. So again, what we are trying to use machine learning for is to get the parameters of these clusters, like what is the interactions, what's the interactions of these clusters. Once we get these V's, which are the interactions, then we can use that for, say, Monte Carlo simulations to do very fast calculations to get the alloy phase diagrams. Okay, if you want to understand the math, this is just a very short, very brief introduction to the Lasso method. So if you look at the first equation, y equals to x dot beta, this is usually used in the least square method. So y is the properties that you want to predict. X is something that we really know, but beta is a parameter that we do not know. So over here in the Lasso method, there's actually a term which is added. This is what we call the regularization term. So so the first term in this equation itself is actually the least squares term. So this is basically the minimization function. So the first term in the minimization function is the least square term, which I think many of us could be familiar with, because we use the least square methods for regression. We use the least square method to fit graphs and everything, and many other things. So what is new over here is just to add a certain penalty function that will drive the solution, which will drive the methods to discover interactions, which is more sparse. Yeah, because over here, the thinking is that if we have too many of these interactions, if we have too many of these effective interactions, then we might run into the trouble of overfitting. Yeah, so if you are familiar with the machine learning literature, we always want to be, we are always mindful that we do not overfit the solution or we do not underfit the solution, right? So we have to be able to balance the machine learning model and the interactions so that we have a good balance in terms of not overfitting. Overfitting means a bias, and to avoid underfitting as well. So I think if you look at the diagram over here, this we show that, for example, in our interactions, if we use group Lasso, we actually get physically meaningful interactions. We know that in material science, usually the interactions, those interactions that is the shortest distance will be the strongest, and further away interactions and multi-body interactions should be the weakest, right? So if we use group Lasso, we actually have this physics actually being built in. You can see that the pair interactions are strong, the triplets fairly strong, but the 4 bodies and 5 body interactions is getting weaker and weaker, right? All right, so this is the result. This is after training the machine learned model. We use the machine learned surrogate model to do Monte Carlo simulations to understand, for example, the short range order of this particular high entropy alloys. What we are tracing over here is that what is the structure, what is the arrangement of the atoms as we go from high temperature to low temperature. So on the right, if you look at the box over here, this is a box of various atoms and atomic configurations. So there will be 5 different colors for 5 different elements. You can see that at high temperature, all these atoms are randomly arranged. So we call it the solid solution phase or the disordered phase. But as you decrease the temperature, increasingly there's more and more segregation. You can see that the vanadium atoms in red and the zirconium atoms in yellow, they will phase separate from each other. And this phase separation becomes more and more prominent as we go to the lower temperature. And we can use this for design. Suppose we want to study different compositions of high entropy alloys. Do we know which composition will lead to phase separation? Do we know which compositions will have a higher chance of having a single phase? So for example, niobium, titanium, zirconium, this is ternary, and then we know that there's some interest in using this for, say, biocompatible applications. And over here is important that this material is a single phase, because we know that if it's usually for alloys, if you have 2 phases, it might not be corrosion resistant. If we are going to use this for, say, bioimplants, then this material needs to be fairly corrosion resistant. And on the right over here, you can see that depending on the amounts of different elements is being added, there could be different degrees of phase separation. Okay, now I switch to another topic, but it's still on high entropy materials. I'm trying to share that we can also apply the high entropy concept to ceramics, to 2D materials as well. Some of us might be familiar with these materials called max phase, and this is essentially a layered kind of materials. It's essentially a layered carbide. So with transition metal elements and carbon or nitrogen for the non-metals. So on the picture on the right over here, you can see that, okay, we have the max phase, and if we etch out, if we remove this aluminum layers, then we can form these 2D materials, right? Okay. And for this kind of alloy magazines, we can see that depending on the kind of transition metal elements that's being mixed, you can have different kind of ordering. So for example, this graph itself is trying to show what is the amounts of transition elements that is being separated to the surface. So if you look at the blue color line, that is titanium, molybdenum. You can see that it likes to form an interlayer ordering, which means that molybdenum likes to be on the surface and titanium likes to be in the middle layer. But for another combination, titanium vanadium, which is a yellow curve, you can see that it likes to be in a disordered phase. So even at very low temperature, this particular magazines like to be disordered, right? So depending on, if you're looking at materials design, if you're looking at alloys design, there are different ways to mix and match different elements, and this will give you different atomic arrangement, and that will affect your properties. And we also apply it to the study of high entropy magazines. So interestingly, if you look at high entropy magazines, we see that the disordering is mixed with what we call interlayer separation. So over here, we study, for example, the distribution of titanium, vanadium, niobium, and molybdenum. And you can see that in these high entropy magazines, even at high temperature, there's already some separation between two of the elements. So you can see that moly and vanadium likes to be on the outer surface, and niobium and titanium likes to be in the inner surface. And the value of this work is because this high entropy magazine is quite a new material, and it's very hard even for experiments to really understand what is the structure and how these elements are being distributed. So from this machine learned surrogate model, we can learn that how these elements have a certain preference for inner layers and outer layers, and within the each of the layers itself, the two elements, like for example moly and vanadium, they are more or less randomly mixed. So the short story over here is that for high entropy magazines, there will be some separation, but within each of the layers itself, the 2 or 3 elements will be randomly mixed. Okay, now I will introduce some applications of the methods to look at designing alloy nanoparticles. We know that properties changes when we go to nano size regime. So when we go to nano size, especially when you go, say, below maybe 50 nanometers, there's the effects of size and the quantum effects comes in. And we know that for catalysis design, we like to have small nanoparticles because we have a good surface to volume ratio. But going to a very small nanoparticles, it will change your chemistry, and that actually complicates our design of catalysts. All right. This is to show that we can use similar methods to study, like for example, we call it adsorbate induced phase separation. So if you look at the diagram on the left, what we are trying to illustrate over here is that for nanoparticles, like for example, if you mix palladium and rhodium as a nanoparticle, if there is no oxygen on the surface, rhodium, which is the brown atom, likes to be in the middle. But once you include some oxygen on the surface, rhodium will preferentially prefer to come to the surface itself. So this is also a phenomenon which is observed in catalysis experiment. Sometimes the catalyst that you prepare, and sometimes the structure that of the catalyst that you prepare will change during the catalysis process. So over here, we show that we have a method in order to study how the adsorbate or reaction intermediates changes the catalyst structure. And we can use that for designing new alloy catalyst itself. If you look at the diagram on the left over here, if you're familiar with Jan Noskov's work, who is a very famous computational catalyst researcher, you can see you can use this kind of a volcano curve to design promising materials. So what the volcano curve is trying to tell you is that they will absorb hydrogen on the catalyst surface, and depending on the absorption energy, which is given by the x-axis, if the absorption free energy delta GH is close to 0, this would be a good catalyst. So it illustrates that for this particular reaction, hydrogen evolution reaction, platinum is a very good catalyst because it is very close to the peak of the volcano curve. And for computational researchers like me, what we need to do is to find a catalyst which can absorb the hydrogen atom in around this absorption range of negative 0.24 eV. So we can use this to design new catalyst materials. So what we show over here is that if we look at platinum and palladium nanoparticles as an example, if you look at the diagram on the left, we can use this kind of machine learned surrogate model to identify what are the stable nanoparticles core shell structures of palladium and platinum. So depending on how much ratio between platinum and palladium, you can see that there'll be some palladium elements on the outer shell, and platinum likes to be in the core, right? So we have this so-called core shell structure. And once you have the models, once you have these structures, we can use that to calculate what is the hydrogen absorption energy. You can see that at 100% platinum, because of the size effect, the absorption energy is out of the optimal range. So the absorption energy of hydrogen will be too strong. But as we add more and more palladium going to the left, you can see that it tunes the absorption energy into the optimal region. And likewise, we can use this to study, for example, the we call it the adsorbate interactions. So you can imagine when we are doing, say, hydrogen evolution reaction, the catalyst surface could be covered by different amounts of hydrogen on the surface. And in the catalysis community, there's something called the adsorption isotherm. So we can use this models to study, for example, how the hydrogen absorption and coverage and distribution changes with electrode potential. So the x-axis is the electrode potential. So at very positive electrode potentials, there's not much hydrogen on the surface. But as the electrode potentials gets more and more negative, there's more hydrogen coming to the surface. And from our modeling, we can track, we can identify which adsorption sites gets covered first. So you can see that, for example, in the diagram below, you can see that initially the hydrogen atoms, which is the blue color atoms, actually likes to be adsorbed on the edge of the nanoparticles. As you have more and more hydrogen atoms, they get adsorbed onto the face of the nanoparticles. Yeah, and therefore we can track how the hydrogen prefers to be adsorbed on the nanoparticles as we have more and more H on the surface. And we can also use this to compare what we call the cyclic voltammetry experiments. Because each of these peaks, if you look at the diagrams over here, you have a beta peak, you have delta peaks, and all these peaks are fingerprints. These peaks will tell us that which of these adsorption sites is hydrogen absorbing on. So if we compare the peaks, the position of the peaks, our theoretical calculations using the surrogate models is very close to the experimental ones. And of course, there's ongoing interest in the catalysis community to use to study high entropy materials for catalyst design as well. So the concept of this high entropy materials is being used in is expanding to many other materials research, including high entropy ceramics, high entropy catalysts, and high entropy battery electrode materials. Okay, I think that's the end of my presentation, and I would like to thank my collaborators and colleagues from IHPC and also from Iowa State University. Okay, thanks.
Thank you very much, Dr. Teck Liang. I think we've learned a lot from you today, and I think everyone can help, congratulate and thank you by sending some reaction there for Dr. Teck Liang. And I think we have a few minutes for the question and answers. And before we begin the Q&A session, I'd like to say a few words about what we've learned, how at the IHPC, you and your co-workers and the collaborators have showcased for us here today the development of the machine learning and surrogate models, and to study the structural representations of the high entropy materials. And that can sort of like leading to a prediction of the properties. That's what the material science and engineering is all about. So let me begin by asking if anyone has some question here. Please, you can turn on your video or turn on your microphone and ask Dr. Teck Liang directly. I think we have about 4 or 5 minutes here. Thank you.
Can ask a question. Hi, it's PJ Thongjaishu from MTech. Hi. So in your talk, hello, you talk about binary phase diagrams, right? And then you also covered high energy alloys. And I was wondering about the high energy alloys phase diagram, because you kind of show one of the phase diagram that looks like a ternary phase diagram, but it's actually for a high entropy alloy. So I was just wondering if there's any database already for high entropy alloy materials for phase diagrams, because I think that would be really neat. Okay,
I have to qualify this statement. Thank you, Thongjae, for the question. So, so there are different ways to get the phase diagrams. You can use the DFT, and which I showed over here. You can also use a method called the Calvert method, which is a calculation of phase diagrams. Okay, so typically, over here, what we try to do was to do a direct calculations. That means I really do a high entropy alloys model and I calculate its properties. So there are ways. There are also other ways to do what we call extrapolation. So we have databases for binaries and ternaries. So some people, some community out there, they will use this knowledge of binaries and ternaries and extrapolate it to say the prediction of phases in the high entropy alloys, whereby you have 5 or 6 different elements. So we call it the how should I say, the extrapolative methods. Yeah, I'm not sure if I fully address your questions, but there are ways to use, let's say, binary and ternary data to do some predictions of phase diagrams for high entropy alloys. Then the question would be, how accurate is this predictions? So I think it's like an ongoing research topic, and that is very interesting. So thank you so much for sharing this to us. Yeah.
Yes, is there any other question from the participant to Dr. Teck Liang on the his talk? If yes, please, maybe you can raise your hand or just turn on the microphone and just speak. Okay, if not at the moment, I think we have heard a very excellent talk and very illustrious presentation from Dr. Tan Tek Liang from IHPC in A-STAR. Thank you so much. Thank you.
Thank you. Yeah.
Thank you.
Thank you.
Okay, moving on.